Welcome back to Med Simplified Hab, everyone. Today, we're diving into a special explainer focused entirely on the absolute VIPs of human movement, your synovial joints. If you've ever wondered how you're actually able to throw a baseball, thread a tiny needle, or, just nod your head, well, you are in the exact right place. We're going to break down the incredible biological engineering that allows us to move through the world with such fluid grace. Now, here at Med Simplified Hub, we like getting straight to the good stuff. So today, we're completely skipping over those rigid, fibrous joints, like the immovable sutures holding your skull together, and we're bypassing those slightly yielding cartilaginous joints in your spine. Instead, we're diving exclusively into the diarthroses. These are the freely movable marvels of our skeleton. They provide the vast majority of our body's movements, giving our limbs an absolutely incredible range of motion. So here's our roadmap for today. First up, the joint blueprint. Second, the 6 joint types. And finally, joints in action.
Okay, let's jump right into section 1, the joint blueprint.
Before we look at how, say, a shoulder differs from an ankle, we really need to understand the fundamental shared design that makes these highly mobile joints possible without just grinding our bones to dust. The defining feature is that there's an actual space, a joint cavity, right between the articulating bones. They aren't directly connected to each other by solid tissue. Instead, an articular capsule forms this neat sleeve of fibrous tissue that holds the bones close. And look at the ends of those bones. They're coated with a super smooth layer of hyaline cartilage. In younger folks, this cartilage can be up to 7 millimeters thick. It provides a beautifully slick surface, reduces friction, and absorbs the massive compression forces of our body weight. But here is the catch. That cartilage has absolutely no blood supply of its own. So how on earth does that bloodless cartilage survive? Well, that brings us to synovial fluid. The synovial membrane, which is an epithelial layer lining the inside of the capsule, secretes this vital fluid. It's thick, it's sticky, and it literally has the exact consistency of raw egg whites. This fluid is a total multitasker. It nourishes the structures inside the joint, contains phagocytes to clean up cellular debris and microbes, and acts as a brilliant lubricant. In fact, it prevents the ends of the bones from separating, working exactly like a thin layer of water trapped between 2 flat panes of glass. It essentially holds them together while letting them slide effortlessly. To support that basic blueprint, our bodies add some extra hardware depending on what the joint actually needs to do. Think of these as the ultimate biological shock absorbers and stabilizers. We've got little sacs of synovial fluid called bursae, and they act as cushions so your skin, ligaments, and bones don't just rub together. Inside the capsule, some joints have fat pads and menisci to better stabilize the load. And outside the capsule, we have strong ligaments blending with the joint sleeve, plus muscle tendons stretching right across the gap. When a muscle contracts, it shortens, pulling one bone towards the other, and boom, you get movement. Moving right along to section 2, the 6 joint types. While every single synovial joint shares that fluid-filled blueprint we just talked about, the actual shapes of the bone ends dictate exactly how they're allowed to move. We functionally classify these joints based on the number of axes they move across, meaning anatomical planes, like transverse, frontal, and sagittal. Uniaxial joints, they only allow movement in a single plane. Biaxial joints let you move across 2 planes, and the highly complex multiaxial joints allow for movement in all 3 planes, plus rotation right along the limb's long axis. Let's break down the specific shapes making these movements happen. Let's contrast 2 extremes here. On one hand, we have the multiaxial ball and socket joint. Picture the head of your humerus sitting in the cup-shaped socket of your shoulder. It allows an incredibly wide range of movements: flexion, extension, adduction, abduction, rotation, you name it, even circumduction. But because it's so incredibly mobile, it is our least stable joint. It's highly prone to dislocation. On the totally opposite extreme, we have the uniaxial hinge joint. The articulating ends fit together exactly like a literal hinge on a door. Take a second and actually flex your own elbow right now. Feel that? The mechanics restrict your form exclusively to flexion and extension. It's incredibly stable, for sure, but tightly restricted to that single plane. Next up, we have pivot and gliding joints. These provide subtle yet absolutely essential mechanics. In a pivot joint, a bone fits into a hoop-shaped ligament, allowing it to rotate. This is literally what allows you to shake your head no. The dens of your axis bone acts as a pivot inside a ring formed by your atlas bone. Then we have gliding joints. Here, the bone surfaces are flat or maybe just very slightly curved. They basically just slide over one another. This is the least movable type of synovial joint, found tightly packed between the carpal bones in your wrist or the tarsal bones in your feet. Which brings us to our final section, Section 3, Joints in Action. The sheer density of joints in our extremities is wild. Just look at the complex architecture of the hands and feet. Between your metacarpals and your phalanges, so your knuckles, you have biaxial condyloid joints. A smooth, rounded projection of one bone sits perfectly inside a cup-shaped depression of another. This highly specific engineering is what allows your fingers to flex, extend, spread apart, come back together, and even trace tiny circles in the air.
But you know, the real star of the human hand is described beautifully by this classic anatomical analogy. Bones fit together like a man sitting on a saddle. This is the saddle joint, and the most important one is right there at the base of your thumb, between the trapezium of your wrist and your first metacarpal. It has the same flexibility as a condyle joint, but with one massive upgrade. It allows for opposition. Opposition is the ability to swing your thumb across your palm and touch the tips of your other fingers. This single joint design is what gives humans our unbelievable manual dexterity. It lets us hold a pen, play a guitar, or seamlessly manipulate tiny objects.
So before we wrap things up today, I want to quickly test your anatomical intuition. Thinking about all the intense forces the human body has to endure, from jumping to running to literally just standing up against gravity, which joint do you think is the absolute largest and most structurally complex in the entire human body? I'll give you a second to think about it. If you guessed the knee, you hit the nail right on the head. The knee takes the crown here. It is an absolutely massive hinged joint formed by the condyles of the femur, the tibia, and the patella. Because it has to bear virtually all of our body weight, it requires maximum stabilization. Deep inside that joint capsule, it houses two cruciate ligaments that literally cross over each other to tie the femur and tibia together securely. And because it's constantly under so much mechanical stress, it is packed with numerous bursa and thick pads of fat to prevent friction between the skin, the kneecap, and the dense network of tendons crossing the joint. It is just a true masterpiece of biological engineering. Which leaves us with this final thought. Every single time you take a step, write a quick note, or just reach for a cup of coffee today, take a second to remember the incredible egg-white lubricated machinery working silently right beneath your skin. Our mobility is a pretty amazing gift made possible by the flawless structural blueprints of our synovial joints. So how will you appreciate the engineering of your own biomechanics today? Thank you so much for joining me for this Med Simplified Hub Explainer. Keep moving, keep learning, and I'll catch you next time.